Good morning. Sorry I'm not there with you guys. It's my turn to stay home with the sick kids. So hopefully you are able to see the Tuesday weekly planner page on your screen. Today, I'd like for you to finish the comparing graphs activity that you started online. So the computers are in the back of the room, and hopefully you remember where you left off. Before we get to that, though, I'd like to go over the giant practice problem that we left off with on Friday. So first things first, the at the bell question says little Larry slides down an icy grass slope in a cardboard box and skids to a stop across the flat ground. If Larry's friend were also in the box, giving it twice the mass and starting from the same height, the skidding distance would be less, the same, twice as far, 4 times as far, or none of the above. What do you think? Let's see. Answer is B, the same. So twice the mass means twice the normal force, and hence twice the friction, both on the slope and on the level ground. So on the slope, with both gravity and friction proportional to mass, acceleration is the same, and the speed at the bottom is the same. Starting with the same speed across the flat ground, with frictional force proportional to mass, acceleration and stopping distance are the same. So if they were traveling at a different speed, then that would switch things up. But here it keeps it in the same balance of forces. And we will get into that probably next week. So on Friday, we left off in our workbook, and question 1 had many, many parts to it. So I'll walk you guys through the answers and then show you what I'd like you to have finished in the AP workbook, the other workbook that has those fill in the blank justifications still. I want to make sure we're up to a certain point in there. You might already be there, so just check and see. And if you're not to that point, go ahead and complete those questions up to that point. All right, so here we have someone using a high intensity interval training. It says describe the motion of the athlete using values from the graph. So you can see that we have an increase, we have a horizontal portion in velocity, and then a decrease, another horizontal, and then another decrease. So the athlete accelerates to the top velocity, maintains that velocity, or stays the same, stays at rest, then decelerates to a lower velocity, maintains that velocity for a period of time, and then decelerates to a stop. So here you could put maintains or constant velocity, since it's a velocity over time graph. During which time intervals does the athlete have a constant velocity? Between 5 seconds and 15, and then again 17.5 to 35. During which time intervals does the athlete have a constant acceleration? So non-zero acceleration. Between 0 seconds and 5 seconds is the first part. During the 15 seconds to 17.5 seconds, even though they are decreasing in their velocity, they're decelerating. It's considered a type of acceleration. And then this last section of the line, 35 seconds to 40 seconds. So anywhere it's not flat. Determine the different accelerations for the time intervals identified in part C. So these are the 3 sets we need to use in the problems below. So acceleration is velocity final minus velocity initial, or you can use v2 and v1 over time final minus time initial. So in section 1, they end at the 12-meter mark to the north, and they started at 0 meters per second, and that takes them the first 5 seconds, so 5 minus 0. So you get 12 meters per second over 5 seconds to the north. So your answer should be 2.4 meters per second squared, or per second to the north. In part 2, where they decelerate, this section right here, you take the 4.5 meters per second to the north minus 12 meters per second to the north, and subtract their time, 17.5 seconds minus 15 seconds. You get 7.5 meters per second to the north. You can see they have a negative because they were decelerating. So it's not enough to just have a negative there or just the north there. Remember, when you're dealing with acceleration, the acceleration doesn't have to be in the same direction as the motion. So even though on the graph the line goes down, the person doesn't change directions, they're just slowing down. The acceleration is no longer going in the same direction as the velocity. The only time they would change directions is if you cross the timeline, across the bottom. So the negative here is important in the second portion because they're slowing down while still traveling to the north. So you'd want to have both for that one. And you end up with negative 3 meters per second to the squared, or meters per second to the north. If you decided not to use the negative and decided to just focus on the acceleration, like which direction the acceleration is going, in this case the acceleration is to the south, and you wouldn't need a negative in that case. So if you were thinking about what the velocity would look like, they're still headed north, but they're slowing down, you need the negative to show that the acceleration is in the opposite direction of the motion. If you are just looking at the acceleration, then you need to change the direction to south, and you don't need to use the negative. I don't like talking to myself on camera, so I hope that made sense. Number 3, again, they are slowing down, still headed north. So 0 meters per second is where they end. They start that section at 4.5 meters per second to the north. It's during the last 5 seconds of the time. So here again we have our negative 4.5 meters per second to the north divided by 5 seconds. And since the acceleration again is in the opposite direction of the motion, we have negative acceleration to the north, or just south acceleration, which is opposite of north. All right. Here they wanted you to find the area under the graph by dividing it into shapes. So you can see that first they determined where some nice rectangles could be. So here we have what looks like almost a square. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Yeah, almost a square. And here we have a slender rectangle. Area 1 is a triangle. Area 2 is a rectangle. Here they cut up this kind of awkwardly shaped area into a rectangle and a triangle. So you have area 3, and then area 4, area 5, and area 6. And on your paper you should show all of the work to find the areas of those different shapes. So area 1 being a triangle is half base times height, and you get 30 meters north. And area 2, since it's a rectangle, is length times width, 120 meters north. Area 3, this little triangle, half times base times height, is 9.375 meters to the north. And if you chose a different amount of significant figures, that's fine. Area 4 is length times width. And again, they chop up those boxes in an awkward way. You end up with 11.25 meters to the north. Area 5, length times width, 78.75 meters to the north. And area 6, the triangle, half times base times height, 11.25 meters to the north. Depending on where you thought these lines kind of lined up, if you didn't catch 0.5s on those, your answers might be a little bit different, but they should be close. So very similar to the other problem that we did together, they want you to find the position of the athlete after a certain increments of time. So at 0 seconds, it's 0 meters. They haven't gone anywhere. At the 5-second increment, they're using area 1. So the displacement according to area 1 is 30 meters to the north. After 15 seconds, right here, that would need to be area 1 plus area 2, 150 meters to the north. At 17.5 seconds, right here, they're going to take this little sliver that consists of area 3 and area 4. So area 1 plus 2 plus 3 plus 4. Get you 170.625 meters to the north. You stopped at 0.6 or 6.2. Probably be fine in this case. 35 seconds right here on our timeline includes area 5, so we have to add area 1 through 5 together. You get 249.375 meters to the north. And the end of the timeline is all of the areas added together, and you get 260.625 meters to the north. So it says, using the information from the previous questions, create an accurate position time graph for the athlete. So they're wanting you to take the data from a velocity time graph. Now you have these positions at given times and turn that into a graph. So you needed to fill in the position increments fitting up to 260. So it looks like they counted by 20s. And it looks like they ignore the decimals on this graph. And you should have a curve, and then what looks constant, curve, kind of a constant, and then a little bit of a curve. And they want you to explain what you did here. So constant velocities are straight lines on the displacement or position versus time graph for 5 seconds to 15 seconds. No, that's wrong. That only goes to 10. So this is wrong, or this is wrong. It would have to be 5 to 15. So it looks like they may have messed up right here on that one part. And then 17, like here, to 35. So it looks like they need to shift these dots over a little bit to make that line up right. Acceleration to the north is a parabola that opens up for 0 to 5. There's a little baby parabola right there. And then deceleration or acceleration to the south is a parabola that opens down. That's this little bend right here. And then the last 5 seconds. There's supposed to be a little bit of a curve there, which is hard to see. So this graph is not drawn well. Hopefully yours looks better. And that is where we will end with checking these questions. Your homework, or homework for today, in the AP Physics workbook, I know talked about the people on the train. And I know that we haven't checked all of the pages that have been assigned, but I would like for you to make sure that you have page 11, which is called constant velocity, page 12, graphs of velocity, page 13, relationships between position, velocity, and acceleration, page 14, relationships between position, velocity, and acceleration, page 15, the chase, page 16, the chase, finished. So up to page 16, finished in your book. We may have already assigned those, I can't remember. So make sure you have those finished. All right, with the time that you have left, please get a computer and go to the challenges of the Graphs and Tracks website, which is linked through the weekly planner that you have access to in the Google Classroom, and pick up where you left off. All right, we'll see you tomorrow, hopefully.